Unit 2, Lesson 8, the Perpendicular Bisector Theorem. Our learning goal is let's convince ourselves that what we've conjectured about perpendicular bisectors must be true. So, the main thing here, or the main idea is perpendicular bisectors. What does that involve? Perpendicular, right, means that we have the whole 90-degree situation, and the bisector means that a segment is cut perfectly in half, right? Bi means two. So this is a quick example of what should pop up in your mind when you hear the word or term perpendicular bisector. Okay, you have your 90-degree angle created by an intersection of two lines or two line segments, and then the segment is cut in half, right? So for example, let's call this point C. AC will be the same length or congruent to BC, right? So they're cut in half. AB is cut perfectly in half. Okay, into two pieces. So remember, bi means two. Okay, warm up, 8.1. Which one doesn't belong? Intersecting lines. So I'll give you some time to gander at A, B, C, D, and come up with your response. Which one doesn't belong? Okay, so hopefully you paused the video and you took some time. I noticed that we had B here indicates the 90 degrees, right? As A does not. And if you notice, even their naming of the lines or line segments, I think they're lines. I don't see the arrows, but yeah, they're switched, right? L and M are in different locations, so that's just something to notice. They're telling us here in part C that these two angles are congruent to each other. Okay, that's interesting. And it looks like they have the same labeling as part B does, right? D uses entirely different lettering, right? Line K and line N, but they do tell us that line K and line N are perpendicular. Okay, that's a symbol for perpendicular, which is an equivalent, if you will, of just saying what B was telling us. Okay, that means 90 degrees. This means 90-degree intersections. Okay, of course, by the other idea or definition of a line, this angle right here is also 180, right? And notice how these are both 90s. Well, that's the same as saying that these two angles are congruent. Okay, so there's a lot of similarity interconnected with all these different figures. So that's just something to note there. All right, activity 8.2, lots of lines. So we have a couple kids here, and they were given a task. They were given a proof where they have to prove that point C is the same distance from A as it is from B, then C must be a perpendicular bisector of AB. Okay, so that's immediately you're just like, what? Right? So these kids, they approached it in several ways. So just by scrolling around, let's see. So let's read the prompt. At first, they were really stuck. Noah asked, how do you prove a point is on the line? The hint that the teacher gave was another way to think about it is to draw a line that you know C is on and prove that the line has to be perpendicular or has to be the perpendicular bisector. So they each drew a line, okay, and thought about their pictures. So we have 1, 2, 3 kids. So there's 3 different drawings. And let's look at the first drawing. So it looks like Diego here says, well, in his drawing, that he drew a line through C that was perpendicular to AB through the midpoint of AB. Okay, that line is a perpendicular bisector of AB, and C is on it. So that proves that C is a perpendicular bisector. Okay, is on the perpendicular bisector. So perpendicular bisector, does he have, so notice how he marked, right, the points there. And for giggles, I'm just going to label this D, all right, although he did not. But he does have the fact that AD in this situation is congruent to BD, right? So he has some sides there that are congruent. He also indicated that there's that 90-degree angle, right? So that's interesting because that's perpendicular, right? And then C is right there. So that was his idea. Okay, he didn't mention D, so I shouldn't probably put words in his logic there. But that's pretty much what he has. Jada, let's see, she says that I thought a line through C would probably go through the midpoint of AB, so I drew and labeled the midpoint D. Okay, that's awesome. Triangle ACB is isosceles, so she's actually using the definition here of an isosceles triangle. And she says, so angles A and B are congruent. So she's saying this angle here and this angle here are congruent. Okay. And she says AC and BC are congruent. So AC and BC are congruent. Okay. That made two congruent triangles. Oh, whoa. She's using side angle side. Triangle congruency theorem. Okay. All right. So do you guys see that? She says she knows these. She knows AD, right, and BD are the same or congruent to each other, right? So she's got two pairs of congruent sides. She knows that she has this angle and this angle being congruent to each other, and then these two sides by the definition of an isosceles triangle. So she definitely has side angle side triangle congruency theorem. So she's actually looking at this as two triangles. There are technically two triangles after she draws the perpendicular bisector. So she says, I know angle ADC and angle BDC are congruent, but I still don't know if DC is a perpendicular bisector of AB. Interesting. So she knows, let me highlight it. This is her issue. She knows that these two angles are congruent. Okay. She knows this angle here and this angle here are congruent. But knowing for a fact that they are both 90 degrees, right? She knows this segment and that segment are congruent to each other, right? Which definitely takes care of the bisector part, but she's not sure about the perpendicular part. Okay. Diego was kind of, he wasn't saying a lot, like in terms of verifying whether or not the line he drew was a perpendicular bisector. Like he knew that the sides, right, had to be congruent there and the 90 degrees, but proving it, it's like, I don't know. Jada's like thinking more about triangle congruency. All right, let's take a look at Noah here. Noah basically says, well, in the isosceles triangle theorem proof, and he's referring to his friends from, I think, a previous lesson, drew an angle bisector. All right, so an angle bisector basically cuts an angle in half, right? And that actually gives us a pair of congruent angles. Okay. And then he says, I'll draw angle bisector of ACB, which is, let me highlight that for you, angle bisector of ACB. So he basically draws us this line right here, and it cuts the angle in half, right? Angle ACB. The point where the angle bisector hits AB will be point D. So there's point D. Okay. So triangles ACD, which is the first triangle to the left, right, and BCD are congruent. which means AD and BD are congruent. Whoa, so he's saying a lot. He's saying these two triangles are congruent to each other, right? The left triangle and the right triangle are congruent to each other. And what else? Then he says, because he knows that these two triangles are congruent, he knows that AD, this part, is congruent to that part. Okay. And then CD is the perpendicular bisector. Okay, let me read that again because I'm trying to understand what he's saying here. He does have his angle bisector, right? And the points where the angle bisector hits AB will be point D, right? So triangles. How is he making these triangles, right? How does he know that these two triangles are congruent? That would be my question to him. Like you got those angles by the angle angle bisector. You have these two sides, or at least he stated these two sides. But how does he know these two triangles are congruent? All right, he didn't say anything about DC, did he? He just says it's the perpendicular bisector. What do you guys think? All right, so who do you think has the best reasoning behind this? I mean, I think there's a mixture, right? Like Jada's using side angle side triangle congruency. I thought that was clever. All right. And then this kid was approaching it with an angle bisector. All right. All right, so let's take a deeper look in activity 8.3, not too close, not too far. So we're supposed to be drawing our own diagrams, so hopefully you use the diagrams I already give you. And you're trying to prove this statement. If P is a point on the perpendicular bisector of AB, all right, segment AB, prove that the distance from P to A is the same as the distance from P to B. Okay, so perpendicular bisector gives us several things. First off, by definition, bisector means it cuts AB perfectly in half. That means this side is going to be congruent to this side, right? So AM is going to be congruent to BM. And again, I'm just focusing on the left picture for right now. We do know this is got to be 90 degrees. And this angle here also has to be 90 degrees because the definition of a line, right? A line is supposed to have 180 degrees. If you have 90 here, the missing piece is 90 over here, right? And that's also the definition of a perpendicular bisector, right? What do we know about PM, right? PM is congruent to itself, right? Because both these triangles, the left triangle, AMP versus BMP, they both share MP as one of its sides. So we know this angle and this angle have to be congruent. So we have side, angle, side, side, angle, side. All right, that means these two triangles are congruent by side, angle, side. So let me go ahead and write this out. All right, what was given, all right, was the perpendicular bisector of PM. All right, PM is perpendicular bisector. Okay. Of AB, I should say. All right. So first things first, we know that AM is congruent to BM. And that's by the definition of a, that's the definition of bisector, right? I'll just go ahead and say perpendicular bisector since that's what they gave us. All right. And that's that's a side, all right? That gives us a side. Second, we know that angle AMP is congruent to angle BMP, right? For the same reason, definition of a perpendicular bisector, which does contain that 90-degree angle. So that gives us a pair of angles. Step 3, we know that MP is congruent to itself, since that's the reflexive property. Okay, both those triangles are sharing the same line. Now, since we have side angle side, we can finally say that triangle AMP is congruent to the other triangle, triangle BMP, and that's again since side angle side triangle congruency. Okay, and since those two triangles are the same, we can say finally, and this is the part that we're trying to prove, that AP is congruent to BP since CPCTC, which again means corresponding parts of congruent triangles are congruent. And again, that just means that if these two triangles are congruent, right, the triangle AMP versus triangle BP or BMP, all right, since those two triangles are congruent to each other, all their parts that are corresponding to each other have to be congruent as well. Okay, so that would be a very good proof, step by step, on why AP would be congruent to BP. Now, notice this one. Notice this image. Are they using side angle side here? Could you use something else? So this person did a construction, right? We know that AP and BP are both congruent because they're the radius of the same circle, right? Or a circle with the same radius, I should say. So you could use several things here. You could use, for this, you could still use the reflexive property for knowing that MP is still congruent to itself, right? Definition of a bisector gets you this side, right? The construction can give you the fact that these radiuses are the same length, right? A length of AB, right? Both of them have the same. So you can actually use side, side, side if you wanted to explain that AP is congruent to BP. So constructions, you can still use constructions if you really wanted to, all right, to help prove it, help prove that P is same distance from A to B. Okay, so notice how you can use constructions and you can still use triangle congruency proofs, all right, to make sense of it. All right, so in summary, the perpendicular bisector theorem, all right, is, let's see, the perpendicular bisector of a line segment is exactly those points that are the same distance from both endpoints of the line segment. So very much connected to the proof here, proving that AP is congruent to BP, all right, that idea. So this idea can be broken into two statements. If a point is on a perpendicular bisector of a segment, then it must be the same distance from both endpoints of the line segment. So basically, in this situation, AP is congruent to BP. That idea. If a point is on the same distance from both those endpoints of the line segment, then they must be a perpendicular bisector of the segment. Okay, so it's kind of like, yeah, it's pretty much the converse. So if you guys notice, these two statements are converses of one another. All right, do you notice how they change the logic here? They're basically saying if the point is on the perpendicular bisector of a segment, then it must be the same distance for both endpoints, right? And then they say if it's the same distance from both endpoints of the line segment, then it must be a perpendicular bisector. So this was saying if P, then Q. Well, the converse is, well, if Q, then P. So they just kind of reversed their statement. So again, this is the idea of a converse. So basically, if P, then Q, the other part, is swapped. Okay, so let me clean this up a little bit more. So these two right here are what we call converses. All right. So just be aware that that is the idea of a perpendicular bisector theorem. All right. So if you look at this picture here, we know that this side is congruent to this side. If we're given the fact that this point is on the perpendicular bisector of this given segment, we'll call it AB. Okay, and the converse is if these two sides are the same, okay, or the same distance from the line segment, then we know that this point is on the perpendicular bisector. Okay, that's the end of the lesson. Have a beautiful day.